saw that the compressive strength in terms of the critical buckling stress versus the slenderness ratio looks like this. And limited by the material strength Fy, and that the real curve is something like this, given by AISC strength equation. So if we want to calculate the design strength of a column, we take the critical compressive stress FCR and multiply it by A, and that gives us the nominal compressive strength. And we know that in order to account for variability in material properties and cross-sectional properties, we need to account for that by a resistance factor phi. And so phi times Pn is the design strength of the column. So instead of first using the AISC strength equation to get FCR, multiplying by A and multiplying by phi, which for compression is 0.9, the AISC manual for certain cross-sections and material types provides tables from where we can directly look up phi times P sub n. Here's an example of these tables. So for example, if we wanted to look up the compressive strength of a W8 by 31 column of effective length 15 feet, we can simply go and look it up as phi times P sub n is 230 kips. So a column made out of a W8 by 31 cross-section of yield stress 50 ksi and of effective length 15 feet, we can look up the compressive strength directly as 230 kips. Now, just to understand how this chart works, I have copied the length and phi times P sub n into this Excel spreadsheet. So if we plotted these two, we see that we get the kind of compressive strength curve that we talked about a little bit earlier. Let's look at an example of how to use these tables. Suppose we want to design a column in which the axial load due to dead load is 160 kips and the axial force due to live load is 330 kips. And the effective length equals 14 feet. And we want to select a W14 section of A992 grade 50 steel. What this means is that the compressive yield strength is 50 ksi. So before we can go look it up in the tables, we need to do the AISC 7 load combinations. So let's look at 1.4 times dead load. That works out to be 224 kips. And the other load combination, 1.2 times dead load plus 1.6 times live load, works out to be 720 kips. So clearly this controls. We can now go look in the tables. We want to find a W14 section, 50 KSI steel, effective length 14 feet. We find that W14 by 873 for an effective length of 14 feet has a compressive strength of 10,600 kips, which is much larger than we need. So we don't need this heavy a section. We can look for a lighter section. So we keep looking down the line, and even a W14 by 455 has a strength of 5,420 kips, which is much larger than what we need. So we go on to the next page, and we see that even a W14 by 159 for 14 feet of effective length has a strength of 1850 kips, much larger than what we need. So we go to the next page. 14 by 90 has a strength of 1030, so we're getting close. And if we look at a 14 by 82, it has a strength of 772 kips. If we go any lighter, then we don't have, the strength is less than 720 kips. So we can select W14 by 82. So we can use W14 by 82 section, whose design strength Phi times Pn equals 772 kips. That completes the design of the car.